So this is section 6.1, which is about composite functions. Composition is another operation that we can perform on functions. If you might remember from earlier in the semester, we learned about addition, subtraction, multiplication, and division of functions. But this is composition. We use a special symbol for composition. It's this little open circle. So this is F composed of G. F composed of G. And really what it means is that you're taking the second function and you're plugging it into the first function. So you're having f of g of x. So g of x gets plugged into the f function. So f of g of x. And there's a little bit more detailed explanation and kind of some of the logic behind this that you can find in your textbook. Just look it up in section 6.1. It's pretty straightforward. Now, composition is not too bad. The thing that can be tricky is finding the domain. First off, you need to make sure that x is in the domain of g, and you also need to make sure that g of x is in the domain of f. So you have to actually check two different things, and it can make it a little bit tricky. Alright, so let's look at some examples here. Example 1 asks us, suppose that f of x equals 2x squared minus 3, and g of x equals 4. Part A asks us to find f composed of g of 1. So what this is this is f of g of 1. And when you do this, you want to find this inner function first. So you want to find the g of 1 first. So take 1 and plug it into this g equation. What is 4 times 1? Well, 4 times 1 is 4. So now we have f of 4. That means we plug 4 into this equation. So I'm going to pull up my calculator here, move it over to the side. Maybe I can move it over to the side. So we're going to do let me clear all that out. 2 times 4 squared minus 3. So we get 29. And so that would be our answer. The idea is you do the inner function first, and then you do the outer function. Okay. Next one is g composed of f of 1. So this is g of f of 1. Notice the order of the letters did matter, because in the first one the f came first, the g came second, and so the g was inside. This one, the f came second, so the f is inside. Alright, so let's find f of 1 first. So we're going to plug 1 into that equation. So 2 times 1 squared minus 3 gives us negative 1. So now we have g of negative 1, so plug negative 1 into this g equation. 4 times negative 1 is negative 4. Okay. F composed of f of negative 2. So this is f of negative 2. So we want to find the inner part first. So we want to find f of negative 2. So we're plugging negative 2 into this f equation. 2 times negative 2 squared minus 3, we get 5. So now I have f of 5, so I'm plugging 5 into the f function. 2 times 5 squared minus 3, we get 47. Excuse me. Alright, our last one for example 1, we have g composed of g of negative 1. So this is g of negative 1. So we're going to do the inner part first. So we're going to find g of negative 1. 4 times negative 1 is negative 4. So now we have g of negative 4. Plug that in. 4 times negative 4 is negative 16. It's pretty easy to do composition when you're just doing numbers, because it's just a matter of plugging in and making sure you do them in the correct order. Okay. Now let's do a little bit of it with some functions. So example 2 gets us, given that f of x equals 3x minus 4 and g of x equals x squared minus 2x plus 6, find each of the following. part A, we have f composed of g of x. So that's f of g of x. Now, what is g of x? Well, it's this equation. So really what we have is f of x squared minus 2x plus 6. So just replace what was inside here, the g of x, with what g of x equals. So now this is what we're plugging in. This whole big thing is what we're plugging into the f function. So we're going to have 3 times x squared minus 2x plus 6 minus 4. So that's 3x squared minus 6x plus 18 minus 4, which gives us 3x squared minus 6x plus 14. Okay. Example B, we have g composed of f of x. So this is g of f of x. So this is a g, and inside of it is f of x. Well, here's our f of x function right here. It's 3x minus 4. So we're taking 3x minus 4 and we are plugging it into the g function. So I have 3x minus 4 getting squared minus 2 times 3x minus 4 plus 6. Now, for this one right here, you have to remember that you're doing 3x minus 4 times 3x minus 4. You're actually squaring it out. So 3x times 3x is 9x squared. 3x times negative 4 is negative 12x. Negative 4 times 3x is also negative 12x. So you're going to have negative 24x. And then negative 4 times negative 4 is positive 16. So that takes care of this 3x minus 4 squared. Then we need to take this negative 2 and distribute it into the parentheses. So negative 2 times 3x is negative 6x. Negative 2 times negative 4 is positive 8. And then we still have 8 plus 6. And then the last thing to do is combine like terms. So we have 9x squared. Negative 24x and negative 6x makes negative 30x. 16 plus 8 is 24, plus 6 is positive 30. And so there is my function. Alright. Part C asks us to do g composed of f of 1. Now, there's actually two different ways to do this. I'm going to kind of show you both ways. The first way is, we just found g composed of f of x up here in part B. So when we see g composed of f of 1, it's just telling us to plug 1 into this function we just found. So we have 9 times 1 squared minus 30 times 1 plus 30. Negative 30 times 1 is negative 30. Plus 30, those are going to cancel out. And then 1 squared is 1 times 9 is 9. So that's one way to do it. But we could also do it like we did in example 1. We could rewrite this as g of f of 1. And then we could figure out what f of 1 is. So if we plug 1 into this f function, 3 times 1 is 3. 3 minus 4 is negative 1. And then all we got to do is plug negative 1 into this function. So we have negative 1 squared minus 2 times negative 1 plus 6. Negative 1 squared is 1. Negative 2 times negative 1 is positive 2. So 1 plus 2 is 3, plus 6 is 9. Notice we get the same answer either way. They both come out as 9. Because algebraically we're doing the same thing. We're just doing it in a slightly different way. Okay. So, that's some more composition. Alright. Now let's talk domain, because this is where it gets a little trickier. Okay. When we look at composite functions, you have to look at a couple things. First off, if x is not in the domain of g, meaning the domain of the second function, then that x cannot be in the domain of the composite. Also, any x for which g of x is not in the domain of f must not be in the domain of the composite as well. So any x that would have made g of x equal to something not in the domain of f must not be in the function either. So you kind of have to look at your domain restrictions for f, use those to figure out what values can g of x not equal, and also look at domain restrictions for g. Kind of confusing. So here, let's look at a couple examples of this. Hopefully we'll straighten it out a little bit. So we're given f of x equals 2 over x minus 1, and g of x equals 3 over x. And they ask us to find f composed of g of x and its domain. So that means we're finding f of g of x. So really we're finding f of 3 over x, because that's what g of x is. G of x is 3 over x. So take 3 over x, plug it into your f function. So we have 2 over 3 over x minus 1. This creates a compound fraction situation, so I'm going to clear it up by multiplying through by a common denominator. So multiply this by x, multiply this by x, multiply this by x. And so we get 2x over, here the x's would cancel, and we'll have 3, minus, over here, 1 and x, those, work together, we get x. Okay, so we have 2x over 3 minus x. Are we okay there? Alright, so first thing, this is our function. Now we want to find its domain. The first thing you want to do is you want to figure out your restrictions for g of x. So what number can I not plug into g of x? Well, I can't plug in 0 because I can't divide by 0. So x cannot equal 0. So over here, when we do our domain, that is also a restriction over here. Okay? X cannot equal 0. Alright. The next thing is to figure out your domain restrictions for f. Look at your f function. Your f function has a restriction in the domain. X cannot be 1, because that would make it 0 on bottom. So you know x cannot be 1. Here's the thing. This is not a restriction of your composite. But this number helps you find one. Take this number and set it equal to this function. Take that number 1, set it equal to the g of x function. So 1 equals 3 over x. Now solve for x. We'll multiply both sides of this equation by x. 1 times x is x. Over here, x and x cancel out, so we get 3. This is your domain restriction. Just right here. So we need to add that to our list. It can't be 3. Now, the second one you can kind of see here in the function. If it was 3 and you plugged in, you'd have 3 minus 3, which would give you 0 on bottom. Okay? But this is why it works, because f, in your f function, your x couldn't be 1, but we don't have an f function anymore. We have a composite that has g plugged in. So we need to figure out where does this g function equal 1, because 1 causes the problem in f, and so we kind of set them equal to each other and solve. It can be a little confusing. It's not terrible, but it's just a little confusing is all. Alright, let's look at example 4. Example 4 says, suppose that f of x equals 1 over x plus 2, and g of x equals 4 over x minus 1. Find f composed of g and f composed of f, and then find the domain of each composite function. So we're kind of doing two separate problems here. Start with f composed of g. So that's f of g of x. Or more specifically, it's f of 4 over x minus 1. So if we plug that in, we're going to have 1 over 4 over x minus 1 plus 2. Again, that gives us a nasty compound fraction, so multiply through by the denominator. So multiply this by x minus 1, multiply this by x minus 1, multiply this by x minus 1. On top, 1 times x minus 1 is x minus 1. On bottom, these x minus 1's cancel, and we just get a 4. Plus, here, 2 times x minus 1 is 2x minus 2. And so if we simplify that, we have x minus 1 over 2x plus 2. So there is our composite function. Now we want to find the domain. So first off, we're going to look at restrictions for g. So look at this one. What can g not equal? Well, x can't be 1 there, because if it's 1, we get 0 on bottom. So that is a restriction on our composite. The x cannot equal 1. Then we want to look at f of x. What can x not be here? Well, x cannot equal negative 2, because that would make this function be 0 on bottom. But again, this is not a restriction on our composite. It's just a restriction on the g. So we take that, set it equal to our g equation. So negative 2 equals 4 over x minus 1. And then we're going to solve that. So let's multiply this side by x minus 1. Let's multiply this side by x minus 1. So negative 2 times x minus 1 gives us negative 2x plus 2. Over here, the x minus 1's cancel, and we just have 4. Subtract the 2 across, negative 2x equals 2. Divide by negative 2, x equals negative 1. And so there's our other restriction, x cannot equal negative 1. Okay. So there was the first one they asked us about. The second one they asked us about is f composed of f. So we have f of x. So this is really f of 1 over x plus 2. So we're taking that and plugging it into itself. So we have 1 over x plus 2 plus 2. Again, that creates a compound fraction, so we'd want to multiply through by a denominator. So let's multiply everything by x plus 2. So on top, 1 times x plus 2 just gives us x plus 2. On bottom here, the x plus 2's would cancel, and I just have a 1. Plus 2 times x plus 2 gives us 2x plus 4. And so if we clean that up, we have x plus 2 over 2x plus 5. Okay. So there's our composite function. And then the other thing we want to do is find its domain. Now this time we don't have a g function, but f is kind of acting like the g did. G was the second function here, so f is the second function here. So we want to look at f of x. What can x not equal? X cannot equal negative 2, because that would make the bottom of this be 0. So we know x cannot equal negative 2, because that's the restriction on the second function. Now, we're going to do f of x again. We know x cannot equal negative 2. And this time we're going to set that equal to the second function, which is also f. So we're going to say negative 2 equals 1 over x plus 2. Multiply both sides by x plus 2. So on the left-hand side, negative 2 times x plus 2 is negative 2x minus 4. On the right-hand side, the x plus 2's cancel out, and we just have 1. Add the 4 across, and you get negative 2x equals 5. And then if you divide by negative 2, x equals negative 5 halves. And so there is our other restriction. And again, you can kind of see that in your composite there. If you plugged in -5/2, 2 times -5/2 would give you -5, plus 5 would give you 0. So it kind of makes sense that there's a problem there. Domains with composites can be a little tricky, but they're not too bad. Alright, let's look at example 5. Example 5 says, if f of x equals 3x minus 4 and g of x equals 1/3 times x plus 4, show that f composed of g of x is equal to g composed of f of x, which is equal to x. Another way of saying this is, show that f of g of x equals x, and show that g of f of x equals x. So show that they're both equal to x. So let's do that. So first off, we'll do f of g of x. So that means we're doing f of 1/3 times x plus 4. So we take 1/3 times x plus 4 and plug into this function. So we have 3 times 1/3 times x plus 4 minus 4. Now, what is 3 times 1/3? Well, those just kind of cancel each other out. So you end up with x plus 4 minus 4, and then the plus 4 minus 4 can cancel each other out, and so you get x, which works out. Alright. The other one we have is g of f of x. So this means we're doing g of 3x minus 4. So take 3x minus 4 and plug it into the g function. So we have 1/3 times 3x minus 4 plus 4. The minus 4 and plus 4 can cancel out. So we really just have 1/3 times 3x. And 1/3 times 3x gives us just x. So there we go. We proved that they both equal just x. That this composition equals x, and this composition equals x. You might have noticed at the end of this example there's a note that says this is really relevant for 6.2. In 6.2 we're going to be talking about inverse functions. And one of the ways to prove that functions are inverses is to do these compositions of the functions and prove that they both equal x. If they both equal x, then the functions are inverses. So here, f of x and g of x are inverses. Now, we'll learn more about inverses in 6.2, but this is kind of a good way to connect the composite stuff you've been learning about here in 6.1 with what you'll see in just a little bit in 6.2. Alright, the last thing we're going to look at in 6.1 is decomposing functions. Okay? Decomposing functions is where you take a function that is a composite and you break it back down into two functions. Usually what this involves is looking for an outer function and looking for what is inside of it. So as an example, if we have a composite function, h of x equals 3x squared minus 4x plus 1 raised to the 5th power, this right here, the 3x squared minus 4x plus 1, it is a function that is inside of another function which is just a 5th power. So we could actually take this composite and we could decompose it back into two functions. The outer function, which is the x to the 5th power, and the inner function, which is the 3x squared minus 4x plus 1. If you take this inner function, g of x, and you plug it into this outer function, f of x, you end up getting the original h of x. Okay. And so that's really how it works. You're just kind of looking for what's on the outside, what's on the inside. So let's do some examples of this. Example 6 says express h of x as the composition of two functions. H of x is equal to the cube root of x squared plus 1. So we want two functions, f of x and g of x. Now g of x is usually the easier one to determine. What is on the inside? Well, on the inside is x squared plus 1. Now, what is it inside of? X squared plus 1 is inside of a cube root, so my outer function is the cube root of x. There we go, we decomposed it. And again, you can kind of check yourself. If you take this function and you plug it into that one, Will it give you the original equation you had? Yeah. Two more examples, and then we are done with 6.1. Alright, example 7 says express h of x as the composition of two functions. So we have h of x equals x squared plus 1, all of that raised to the 50th power. So we want to break this down into two functions, f of x and g of x. G of x is our inner function. What is on the inside here? Well, on the inside is x squared plus 1. What is it inside of? It's inside a 50th power, so our outer function is x raised to the 50th power. There we go. And again, you can check yourself. If you take this function and you plug it into that one, you do get h of x, which is our original problem. Alright, last one. Example 8 says express h of x as the composition of two functions. H of x equals 1 over x plus 1. So we want f of x, and we want 2x. Alright, this one's a little trickier, but most people see it usually. Inner function, it's x plus 1. It's this part right here. Now what is it inside of? It's inside 1 over x. 1 on top, and then there's stuff on bottom. This x plus 1 would get plugged in for that x on the bottom, and that would give you your function. Okay? So not too bad. Alright, so that is it for 6.1 notes. As always, if you have questions on the homework, please feel free to shoot me an email.